Today we are going to discuss about convolutional neural networks, a different neural architecture that is bit uh, different from the feed-forward neural networks which we have learned up to now. In the feed-forward neural networks, we have learned how they are working, and that means how they are making predictions and how they are learned, right? For example, say if you have three neurons in this layer and three neurons in the second layer and so on, in the fully connected neural networks, this neuron is connected to all the three other neurons in the second layer, right? This neuron is the same, it is also connected to the all the neurons in the second layer. This neuron is connected to all the neurons in the second layer and so on, right? So suppose there are two inputs, something like this. So all the inputs are connected to the first layer, right? So that is why each of these layers are known as fully connected neurons, right? Neural network. So this is the first layer. This is the second layer, right? So this can continue, right? So, so convolutional neural networks don't need this much connections to connect to the second layers, uh, to the subsequent layers, and so on. And it is trying to do some kind of optimization when the number of x variables are very large, right? So, so these are the input vectors, right? So when the number of x, that means the number of input variables are low, you can use this kind of fully connected neural networks. But when x is very large, say like you are using an image as an input, where each of the pixel values are used as the x variables, then this kind of neural networks should not be practical due to certain reasons, and we will be discussing in this lesson, which is about the convolutional neural networks, which is going to be mainly focused about uh, learning the information that is related to the spatial domain of information. So what is spatial domain? So space is something like this, right? So when it comes to an image, it is a 2D space, right? So you have an uh, x direction and you have a y direction and so on, right? So those are known as spatial information, right? So how to learn spatial information? So because each of the space can be divided into small pixels, right? And these pixels can be represented by x variables. And how these x variables are learned by neural networks. That is when we are going to use convolutional neural networks, right? So we will be in this lesson, first we will be looking at how the real problem that we have with respect to the spatial information that we are going to learn with neural networks, and how we solve these kind of problems uh, in the traditional computer vision subject, which is a bit older subject than the machine learning or deep learning, but which is a computer uh, basically the computer vision was something that was invented at the time when the computing was invented, right? So even before the machine learning or artificial intelligence or anything was there, there were certain algorithms that were developed to identify the images in a space and how it can be represented in a computer. And these concepts are the concepts that got evolved into the level of convolutional neural networks. So we will be learning how the earlier times of computers, computing machines, were identifying the images, and how that representation technique was developed for the machine learning and the deep learning world using the convolutional neural networks. First, we will start with the traditional computer vision problem. Right? Uh, so this computer vision problem is something that people or the computer scientists have invented to mimic the functionality of biological eyes, right? Or biological vision. Right? Uh, Mainly, we were trying to mimic the human eye. So if you think about the eyes of bees or flies and so on, there are many sensing elements. But in this case, we are trying to mimic a human eye or advanced mammalian eye, how it sees an image. Right? So we were going to not we, but the computer scientists were trying to mimic the uh, compute the vision understanding capability with the computers. Right? So what did they do was, so they could, as you all know, the an image consists of smaller elements known as pixels, right? So they have found how to divide a certain image. For example, if it is a face, then you can divide this face into several uh, little uh, spaces which are known as pixels, and each of these pixels can be given certain values. Before, when it comes to the beginning of computer vision, it was about grayscale images or black and white images, as you all know, right? Because in the earlier stages there were no concept of color vision, right? The color vision came later, but the earlier time it was about the grayscale or black and white images, where you have, for each of the pixel there is a certain grayscale value. That means what is the brightness of each of these pixel, right? So maybe this value, it may be, so these values are generally set between 0 and 255, right? So depending on the number of digits that we are going to represent in each of the number of bits that you are going to represent each of the pixels, right? So generally, if you are using 0 to 255, that means when there are 256 uh, numbers that you are going to represent, or 256 levels that you can represent in each of the pixel, right? So you can represent many number of pixels in each image. For example, if it is a say it's 30 by 30 pixels in this direction and 30 pixels in this direction, it would be, how many pixels are there in this image? It's 900, right? So there would be 900 pixels in this image. So in each of the 900 pixels, there would be 255 values, or 256 levels of uh, values that can be included. Right? So these 256, this 90, so this 900 pixels can represent the image, right? By different intensities in each of these pixels. But just representing each of these pixels with a certain value between 0 and 256, between 0 and 256 is not sufficient, right? Because you have to identify a certain, each of these objects in the image, right? For example, this is an eye, this is a nose, this is a mouth, kind of thing, right? So how they were identifying these kind of objects? In the earlier times of computer vision, they found that if we can find the edges of the image, we can identify, we can have a very good meaning or a very good understanding about the image. Right? So what are the edges of an image? Edges means we take the uh, intensity. Uh, so what we can do is we take each of these pixel values as a set of values for the whole image, and when we take a border of a certain object like this one, so you can find, if you uh, draw it in a larger scale, you can find if the outer side is brown and outside is yellow, and this in the face it is brown or something. So there's a uh, intensity difference between these two colors, right? So brown may have a higher, uh, much darker value, so it would be having a lesser value, or this may be for yellow color, it will be having a higher intensity of the image. So this these pixels may be having a value like, for example, 200, something like that, and this area may have the value similar to 100, say example, right? For example, and so when you uh, draw the intensities, you can see that the intensities are rapidly increasing from this region to this region when you are uh, uh, passing from one pixel to the other pixel, from this direction to the other direction, right? So these are the edges. This is how we identify an edge, right? So when you find there's a huge difference between the intensity, there's a drastic intensity difference, you can identify this as an edge, right? So how to identify this kind of drastic changes? You can use the differentiation, right? Differentiation means you take the derivative of this function, for example, right? So however, this is not a differentiable function because this is not continuous if you go to the theory itself, but in this case we don't need to do the formal form of differentiation. What we are going to do is we can use the some filters, right? So filters means you can use some uh, instead of using because all of these values are represented in discrete pixels, we can find what are the pixels that are there in this region, and you can identify what are the pixels that are there in this region. And if you can find the difference between the pixel values, you can find whether there's a huge drop in between these two pixel values, right? So this drop can be represented by the pixel value difference, right? So it's a kind of differentiation, but it can be done in a mathematical or in an empirical way, right? So that means you can reduce this value's pixel value by this value's pixel value, right? This pixels value can be reduced by this value's pixel value. So then if you have a very large number, that means there's a huge gradient difference in this region, and then you can identify this region as a edge, right? So you can identify edges in these directions. So this is a horizontal edge, this is a vertical edge, right? This is a vertical edge, this is an horizontal edge. Similarly, you can once you find the horizontal edges and vertical edges together, and then you merge them together, then you can get the full understanding about this image, right? So that is how the earlier time of machine computer vision was identifying these images. So once you apply a certain filter, say you have a 3 by 3 filter, something like this, right? So you have 3 pixels long, 3 pixels wide, and suppose you have a filter like this where you have 1 1 1 in this direction, and -1 -1 and -1 in this direction, and 0 values in the middle. You can use this kind of filter to identify when there's a huge uh, drastic value decrease, intensity decrease in a certain region, right? Because you can, once you multiply these values with a positive value, plus 1, you get a positive value, and you ignore the middle section, because that's why we are using multiplying them with 0, and then you multiply lower intensity region with -1, right? So then you will get a negative smaller value, right? Say this value is 30, so this value is 20, and this value is, say, it is 10 or something like that, right? So once you apply a filter, this kind of 3 by 3 filter, into a region like this, right, where the intensity drop would be from 20 to 10 or something like that. So then all the pixels in this these pixels would also have a value like this, right? So if you take the 9 pixels that you are going to cover with this filter in this region, it would be like 20, 20, 20, right? So in this region, when it is dropped, it would be like 10, 10, 10, right? So in the middle section, there would be somewhat in between, right? So 15 sometimes, uh, like 16, 18, something like this, right? So you don't worry about the values that are in the middle, right? So that is why we are multiplying them with 0. But once we multiply these 20 values with 1 and add them together, like 20 times 1 times 20 times 1, 20 times 1, you can get 60, right? Times 0 times 15, 0 times 16, 0 times 18, something like that. It's always 0. You don't add them. Then we can add this 10 times. So these values are 10, right? So these are minus 1. Minus 1 times 10, minus 10. Minus 1 times 10, minus 10, minus 10. Then it is plus minus 30, right? So then what would you get is once you add all of them together, it's a plus 30, right? That would be the uh, vertical edge value. So once you apply this filter into a set of pixels uh, like this, you get a mid value. You get the mid pixel value as 30, right? So this is the edge value that you can calculate with this kind of filter, right? When there's a huge uh, intensity gradient between these two pixels, it can be represented by a very large uh, in a large positive value. So then you can identify, yeah, now there should be a edge in this around this filter, right? So when you apply this filter in a region like this where there are no edges, uh, if all the values are the same, like if all the values are 10, for example, then plus 10 minus 10 will be cut off. Plus 10 minus 10 will get cut off. Plus 10 minus 10 will get cut off. Those values would be 0. So then the whole value would be 0, right? So when you apply a filter like this in this kind of area where there are no edges, the value would be 0, right? So there would be positive values when you find a vertical edge. When you find a horizontal edge, the same thing would happen, right? So you can see, you can find different types of filters for these kind of purposes. For example, this is a 3 by 3 filter, right? You can find actually different 5 by 5 filters, 7 by 7 filters, and so on. So you can not this is a vertical edge detector. So you can have similarly horizontal edge detectors as well, right? Actually, you can have diagonal edge detectors as well. So we are not going too deeper into the image recognition, but we are trying to identify how the edge detection problem was developed in the earlier times of computer vision, right? That is the purpose of this uh, theory, so that we can move onto the level how we have developed the convolutional neural networks, right? uh, and when it comes to computer vision these days, which we are going to uh, solve the problems. Uh, so there are mainly several types of computer vision problems that we have to solve, right? So one is known as image classification problems, like the common problem that we say, like have cat images and we have to identify whether this is a cat or not, right? So we can identify whether so this is a binary classification problem. When you are given an image, you have to find whether this image is a cat or whether it is not a cat. or you can have multiple images like cats and dogs and birds and someone, and then when you have given an image, you have to find whether this is a cat or a dog or a bird, something like that, right? So these are also image classification problems. And there are another type of computer vision problems known as object detection problems, where once you given an image of a road, for example, in a computer vision example, right? So you find that you have this road which your car is running, right? And you find there's a crossing line, yellow lines or white lines or whatever, right? And you find that there's a pedestrian who is trying to cross the road, right? And there's a tree by this side of the roads, and there are some branches that are coming to this road. So you once you drive your vehicle in this direction, you have to make sure that you don't hit the branches of this tree, and you have to make sure that the passenger would be crossing the road in next couple of minutes seconds. So you have to detect also there are some cars that are coming towards you, and there's a bus as well, right? So it is coming into your direction. So when you look at this image, you have to identify each of these objects. This is a passenger object. This is a road object, right? These are the pavements, pavement areas, and these are trees, right? These are vehicles. These are yellow lines. You have to identify each of these objects separately in this single image, right? So detecting each of these objects and the nature of this object. For example, this object, this pedestrian is trying to move into this direction. So that is an object with certain uh, attributes in it, right? So there are advanced versions of object detection. So there are levels that you can detect when you look at an image, right? So that is an image detection problem or object detection problem in an image, right? So that is also one of the main problems in computer vision. So this is a new version of computer vision problem, which is known as neural style transfer. When it comes to the earlier computer vision problems that were already solved using some mathematical techniques, this image classification was actually possible to solve to a certain level of accuracy, and the object detection was also possible for some extent, not like the not into the level of human capabilities at all, but with the deep neural networks we could achieve the human level and even surpass the human level when it comes to image classification and object detection. But even before the machine learning was there were computer vision algorithms that could solve these problems. But when it comes to this problem, which is known as neural transfer, neural style transfer, it was actually, according to my knowledge, there were no techniques that were there to apply these kind of filters, style transfer filters for images before the innovation of deep learning and the generative models that we have today, right? So what does this neural style transfer does is actually once you learn a neural network in certain layers, for example, uh, we know that when you are learning a deep neural network, in from here you give the inputs x variables, and from this side you take out the y hat predicted value, right? When you are learning these layers of neurons, each of the neuron layer is learning different form of information, right? So in this layer it would be learning information like the uh, different forms of faces, for example, right? uh, Round faces, uh, somewhat square kind of faces, uh, triangular faces, and so on, right? Large objects, much complex objects will be identified by this layer, right? So, but when it comes to the previous layers, like this layer, it would be learning much less complex objects, something stuff like pieces of the components of a face, for example, the eyes of a person, right? The noses of a person, and the lips of a person, right? These kind of objects may be representing each of the neurons in these levels of depth, right? So in this level of depth, it would be much higher objects like the different types of faces. In this level, different pieces of the face, right? So in this level, it would be much basic stuff like the curves in the face, like these kind of curves, these kind of curves, these kind of curves, these kind of curves, and so on. If there's another layer before that, so these layers would be learning even basic concepts like the edges, right? So like vertical edges, horizontal edges, these kind of diagonal image edges, these kind of diagonal edges, right? So when you look at when you go deeper into the neural network, you can find you start with the much basic edges like the horizontal edges, vertical edges, and then by combining horizontal edges and vertical edges, you can construct somewhat complex objects like curves, right? So if you take, for example, this kind of curve, it may be consists of different forms of this kind of edge plus this kind of edge plus this kind of edge, right? This is so this what does this layer do would be something like by constructing the inputs given by this layer, which have the horizontal edges, vertical edges, and so on, it would construct much complex objects like these kind of curves in this layer, right? In this layer, using several this kind of curves, they would be constructing much complex objects like the eyes, noses, lips, and so on. In a much in the much deeper layers, they would be constructing. They would be using the existing objects like the eyes, noses, and lips, and it would construct the faces in different forms. So this is how the a neural network can learn, right? So by changing some of the layers, for example, if you want to change these layers, and if you want to combine this eyes, noses kind of objects with some other uh, objects like for this one, actually we are using for faces, right? This neural network is trained for faces. You have another set of you suppose you have another neural network for these kind of images, right? Using these kind of images, you have a certain this kind of neural layer, right? So by combining this layer with the face image neural network and the this depth, this much deep neural layer with that is constructed for this type of neural network, you can have a image like this, right? So which is you transfer the uh, objects that are learned in this kind of images, and you can transfer this information into a intermediate layer like this layer, right? From this images neural network, so that you will get a new form of image like this one, right? Which still has the uh, have the features that are relevant to the original image, but some of its neural information are transferred from the other images neural information, right? So you can add the certain values from for this image related neural layers to this layer, right? So then you will get a image like this, right? So that is how you can create this neural style transferred image using deep neural networks. As its name says, we are here using the neural information, right? So before the neural networks, I think there were no successful techniques for implementing these kind of uh, for generating these kind of images, right? So that is another application of computer vision. So this one was a new one, which is unique for deep neural networks. So in the earlier slide, we explained how we can learn a face or another image using a fully connected neural network like this, right? But however, when you are using fully connected neural networks, right, or feed forward networks, the problem is that feed forward fully connected networks basically, right? So feed forward means the information is passing in this direction and there are no cycles in it. So fully connected means you all the neurons in this layer is connected to this layer. All the neurons in this layer is connected to this layer, right? Not only some of the neurons are connected to these values and so on. So then they are not fully connected, right? So fully connected means all the neural neurons are connected to the subsequent layer for all the neurons in the subsequent layer, right? So the problem with these fully connected feed forward networks is that when you increase the input variable, input features x, right? For example, if you have 1 million pixel values that you have to train, right? Say your image has dimensions like 1,000 uh, pixels in this direction and 1,000 pixels in this direction. So then it would contain 1 million pixels in the image, right? So in the today world images, there are many number of millions of pixels in an image, right? And most of them are colored image. So in a colored image, there are three channels you have to store information where general red, green, and blue colors are used for three channels, right? So instead of having single channel, there are two channels more, right? Uh, with the same dimension, right? That means this one is, for example, if it is green, this one is can be used for blue channel, and this channel can be used for uh, red channel, right? Red channel. So there are three. Actually, you have to store not only a single matrix of information, but three matrices, right? So then you would have to have 3 million pixel values you have to use for training this neural network, right? So suppose you have 1,000 neurons at the first input layer, right? So you give this input into a suppose you into a fully connected neural network, and suppose there are 1,000 neurons in this layer, right? So now we know now there are 3 million pixels in all three channels, right? 3 million pixels, 3 million values. And for 1,000 neurons in this layer, you have to have how many number of connections? You have to have 1,000 times 3 million number of connections. So your weight matrix should be having a shape like this, right? So when you train a neural network, you have to remember that, right? So when you are creating the dimensions of a weight matrix, the the weight matrix, for example, for this layer would be uh, represented by the shape in this format, where you have when it is a fully connected neural network, first dimension is given by the number of neurons in that particular layer. That means how many neurons are there in this layer, uh, and the second dimension is relevant to the number of inputs to this layer. Now there are 3 million inputs, right? So this would be the shape of the matrix of the weight matrix for this layer, right? Suppose you have another layer like 1,000 or something, right? So then you would have another matrix that you have to keep the weight values for, the connection between these two layers, right? So if you just think about the number of parameters in this first layer, there would be 3 million times 1000, there would be 3 billion parameters, right? So which is a very large number. So when you want to train a neural network having 3 billion weight values, that means at least there are 3 billion parameters. So that would need a lot of data to be trained, right? So we said that when you are training a neural network, if you don't have sufficient data to train that particular neural network, that means the corresponding to the number of parameters you have much higher number of data points to train, right? Otherwise, your data points would be uh, learned, all the data points would be remembered by the neural network, and that would cause overfitting, right? So when it comes to an image data set, generally you would not have data sets that would contain 3 billion data points, right? That means that you want to have 3 billion data points means at least you should have 3 billion images, but that is not possible, right? Generally you would have lesser number of images, right? Maybe 10,000, 50,000, or maximum it would be several millions, right? 16 million when it comes to the largest image set that were there known as ImageNet. When it comes to the early 2000s, uh, ImageNet was the largest image collection that was there, which is around 16 uh, million. Uh, yeah, as I remember, it's 16 million or some amount of images were there in this image set. So there are 3 billion parameters. So you can't train this neural network without having the problems of overfitting, right? And that is not the only problem, right? So suppose you use some uh, high regularization or something like that, and you come up with the overcome this large number of parameters, but still there would be problems with computation, because this would need a lot of computation power to compute all these 3 billion parameters. And in order to keep this information, keep these weight values in the memory, you would need a lot of memory in your computer, right? So that is another problem that you would have to face, right? Like having 3 billion parameters, if you have at least 1 byte per each parameter, you would need 3 gigabytes of memory for at least to keep the weight values, right? Actually, when you are learning a neural network with uh, with backpropagation, you need much more information to be stored per parameter, right? Some when you are using an optimizer like Adam optimizer, in under general conditions, you would need at least sometimes 6 times to 8 times of information has to be kept uh, more than the parameters. For example, if there are 3 billion parameters, you would need to keep like 3 times 8 billion information bytes of information in the memory, like 3 times 8, 24 billion uh, bytes has to be kept in the memory, right? Because those are including the gradient values and some other information that are relevant to the deep backpropagation process, right? So, you would need a lot of memory just to keep this input layer in the memory, right? So these kind of fully connected neural networks are not practical with uh, image inputs, right? So that is the problem that we have with image inputs, uh, because you need a lot of data first thing, and the second thing is you need a lot of computation power to do it, and you would need a lot of memory to keep the information in the memory, right? So therefore you can't practically you can't use a feed forward networks for large images, right? So uh, you might have heard that how to use a MNIST dataset for classifying the images in image datasets, but these kind of fully connected neural networks can be used for only for smaller images, like for example 30 by 30 images or 64 by 64 images, you can use fully connected networks. But when you are using 1000 by 1000 images and uh, HD images, you can't use feed forward networks. You have to move to some other techniques such as convolutional neural networks. So let's move back into the edge detection problem, right? So this is an image known as this is a very famous image that is used as a standard image for image processing and computer vision using called by the model's name who is displayed in this image known as Lena. Uh, if you want to see so there are different forms of color forms of this Lena image, and there are different forms. Actually, this was taken by one of the earlier scientists in computer vision. Uh, so if you want to see more about more about Lena, you can Google it and see what's the history of the Lena. And I will not explain it here, right? So this is an interesting story, how they have found this image and so on. It should be much interesting if you just see who is this Lena and how this image become a standard image for computer vision, right? So in this image, in this diagram, you can see this. We have taken the grayscale image of Lena, and we have converted this image into edge graph, edge image, right? So in this edge image, you can see that instead of displaying the colors, we are only displaying the edges. That means the gradient values or the edges that are in these images are highlighted in this image, right? So other areas that are having constant values like these regions would be having a black color, right? So these areas would be having continuous value, so they would be having the color black. But when you are changing from uh, one color to the other color, like from here black color to uh, white color, so then there you can see there's a uh, very thick or very bright uh, edge you can find in this edge image compared to the other areas of the image, right? So when you have a very small gradient, the intensity change in this image, say like from here to here, you can find there's a uh, blurred form of edge you can find uh, in this edge image, right? You can find what's bright edges when there are very high, when there's a very significant color change in this edge, right? Like this edge, right? You can find there's a high intensity in this edge. So once you have converted this kind of image into the edge image, then you can use it for processing. So as I explained earlier, you can use a filter that can be applied for all the pixels. You can take, for example, 3 by 3 filter, or this can be also known as a mask. Uh, so this is a 3 by 3 filter of a 3 by 3 mask, like I explained earlier, 1, 1, 1, and minus 1, minus 1, minus 1. So there are different values that you can apply. Not these are not the only values, right? So we will see why we are using the other values as well. So you can use this kind of filter and apply. Start from here. We can apply and move the window a little bit to the right and apply here and apply it here and so on, right? Once you apply all the locations, you can detect whether there's edge, right? So when you have a higher value for by by multiplying with this filter, you can find when there's an edge, right? So this one can identify vertical edges, and you can also draw. You can have another mask, 3 by 3 mask for detecting vertical edges, something like this, right? 1 1 1 1 1 minus 1 minus 1 minus 1. and 0, 0, 0 for this filter, which can identify when there's a huge intensity drop from here to here, right? But when there's a high intensity in this side, and where there's a drop of intensity in this side, that kind of edge can be detected using a filter like this, right? Similarly, you can generate filters for detecting these 45-degree angles, 75-degree angles, negative 45-degree angles, and 20-degree angles, and different filters can be used for identifying different edges, right? So by using these kind of filters and applying and dragging this filter throughout the image, you can you can get an edge image. uh, I mean, you are using, for example, vertical edge image first, and then you draw the second time, you draw another image with horizontal edges, then you combine those two, you can get an image like this, right? So actually, when you are applying an edge to an image, and then you get this kind of image, just by looking at this image, you can identify what is there, right? But this needs a lot less amount of information, right? Because most of the pixel values are 0, right? Because most of the areas are black, and there are only few high intensity values. So this would contain less amount of information than the original image, right? So this is actually a form of compression, image compression, when it comes to uh, image processing, right? So if you want to compress an image, the one of the operations that you can use for compressing an image is using this edge detection, right? But in this case, we are not using the edge detection for compression, but we are using it for other purposes, like identifying the objects, right? So once you have, for example, if you have identified a certain edge like this, right? You can mathematically, if you have found the centroid of this edge here, and once you find all the pixels and find the certain moment around this centroid, you can get a certain value, right? So this value is actually unique to this shape. When you have a shape like this, it would have a centroid like this, and it would have a different moment, uh, different signature around this centroids, right? So we are not going to discuss in detail how these value signatures are calculated, but before the computer vision was there, that is how these objects, different shapes, were detected using edge images, right? So what you have to know is that once you create an edge image out of an original image, you can do much deeper level of computer vision tasks, so that it can identify the objects. For example, using this image, you may be able to identify there's a face in this image, in this region, right? And there's a certain hat in this image. So those are possible once you have converted this image into a much simpler, less information image that contains much detail in a compressed way, right? So when you are applying the filters, that is what we are exactly doing, right? So let's see what actually we are going to do with filters. Like we explained earlier, I will explain it for the second time as well. So in this case, we are using the same vertical edge detector filter. We have ones in this side and negative one for this side. So this kind of filter can be used when there's a high intensity in this side and low intensity in this side, right? So in the middle level of pixels, there would be somewhat intermediate value. So that is why we are multiplying with 0. So once you multiply the high intensity values with +1s and less uh, intensities with -1, if you then you will get a larger positive value. So then that you can identify there's a huge there's a edge where the color is dropped from higher value to a lower value. So once you apply this filter into this image, right? So these are the, for example, take this as the image where each of the value in this image is corresponding to the pixel values of the image, right? This is the this value. This value is the pixel value corresponding to this pixel, which is 3. For this pixel value, the intensity is 0. This pixel value, it is 1, right? So what you can do is you can uh, uh, use this filter and apply it on the image like this, right? And multiply with it, right? So for this filter, actually, first you can apply with -1, -1, -1. These are the values, right? So this is sorry, this is +1, +1, +1. This is -1, -1, -1. These are zeros. So what we do is you put this filter on this image starting from this location, and then we multiply 3 with 1. 3 times 1, 1, plus 0 times 0, 0, plus 1 times -1, -1, plus 1 times 1, 1, 5 times 0, 0, plus 8 times -1, -8, plus 2 times 1, 2, 7 times 0, 0, and 2 times -1, -2. So once you add all these values together, 3 times 1, 3, -1, 2, plus 1, 3, -6, -8, -2, plus 2 will get cut off. I have to calculate it again. So if you calculate it correctly, actually you will get the value -5, right? I'm not going to calculate it correctly, right? So you multiply this one value with this filter, this pixel value with this filter, this mixed pixel value with this filter, and so on. Then we add all of them together, and you will get the final value as -5, which is the value in this pixel, right? So this -5 is corresponding to this pixel, which is the output value of this edge image, corresponding to the original images, this pixel value, right? So once you apply this filter to this region, you get the edge image first pixel, right? So then what you do is you apply the same filter, and you move the filter a little bit left, and then we apply the same values, +1. So instead of having the, let me first erase all these values. And suppose you are using 1, 1, 1, -1, -1, -1, 0, 0, 0. And then you can multiply with these values, right? 0 times 1, plus 1 times 0, 2 times -1, plus 5 times 1, plus 8 times 0, plus 9 times -1, plus 7 times 1, plus 2 times 0, plus time, plus 5 times -1. And then you get the value of -4, right? That is the value that you can get for this value after applying this filter, right? So that is how you calculate the edge image value for this pixel. Similarly, if you want, when you want to calculate this value, you have to move the filter rightwards and apply the filter and calculate. Again, you can move the filter to this side and calculate the value 8 here, right? And then you can move the filter downwards and apply it here and find the values, and then you will get the value -10, and then you move it rightwards into these pixels and you will get -2. With these values you will get +2. With these values you get +3, and then you apply the filter again into these pixels, then you will get 0. And you would apply these values to these pixels and you will get -2. Apply to these values, you get -4, -7, and so on. Right? So what you have to understand is that when you have the original image, so the original image has the dimensionality of 6 by 6, right? So there are 6 pixels this side, and there are 6 pixels in the height, right? 1, 2, 3, 4, 5, 6. But in the edge image, you have got only 4 pixels in this direction and 4 pixels into this direction, right? So what you have really done was you have once you have applied this filter to this image, you have lost some information. Why did we lose this information? Just think about it. Why the image has shrunk into a lesser size once you have created the edge image compared to the original image. This is the reason, right? So once you want to apply this filter to this image, you can only use apply it in this way, right? So in this way, you have to start with this pixel, and then you can move it here, then you will get this pixel value and so on up to this pixel, right? But if you want to calculate this value, you have to move your, or you, if you want to calculate the value of this pixel, you have to move the filter like this, right? But it is not possible, right? Because these values are unknown, right? Because of that, you can't find the values corresponding to these pixels, right? All these border pixels will not be there in the edge image, right? So you will get the edge image only for this set of pixel values, right? The other pixel values will get lost when you are generating the edge image, right? That is a problem with edge detection. So, and we will later see how we can overcome this with using the padding, right? Where you can add a set of pixel values for around this original image, and we can add certain values like 0 values, and you can add a border known as the padding, and then once you apply the filter, you can get the same size of image as the edge image, right? So applying this filter into this original image again and again and getting this new image, it may be vertical edge, horizontal edge, or any other feature, right? in general. So when it comes to the first level of when you apply it into original image, it would be a edge image like a vertical image or vertical edges or something. But even in the middle side, middle sections of middle layers of the convolutional neural networks, you can apply these filters to these images, and you can get new values like this, right? So the, the application of this filter to this image is known as a convolutional operation, right? So you apply this filter using this convolutional operator. This is not the multiplication operator. This is known as the convolutional operator, where you multiply these values one by one, and we take the linear combination of these pixel values with these filter values, and then we take the final value. That operation is known as convolutional operation once you apply it throughout the image, right? So let's move into the an example where you are going to detect an edge which is it's a vertical edge, right? So you can use the similar kind of filter where in this image you can see the intensities in the color itself, right? So plus 10, that means you have a much lighter color, and the 0 you can see much darker, and -1 you can see much darker image, and so on. Actually these colors are not drawn given in the according to the scale to the values that are there, right? So I have just given some grayscale values so that you can get some meaning, right? So not into the scale, but what you can understand is once you first think how you are going to apply this filter into this image, right? So if, for example, if you apply this filter in this section, because all the values are 10, because 10 times 1 times 10 times plus 1 10 times plus 1, they will get the addition would be 30, right? So these tens would be multiplied by -1 -1 -1, it would be -30, right? So in this 30, there would be minus positive 30, this would be negative 30, and middle tens will be multiplied by 0, so it would be 0. So this plus 30 minus 30 would become 0, right? So this value would become 0, which is the output value of the edge image. Similarly, when you are taking these values, also you can find that the pixels are values are 0, right? When you move the filter to the right a little, you can find there's this edge is there, right? So you multiply all these 10 values with 0 filter, so it's 0 value, so it would get 0. These 10 values would get multiplied by 1, and the 0 values will get multiplied with -1s, right? So then it would be 3 times, that means it would be 30, 10 times 1 times 10 times 1 times 10 times 1 times plus zeros plus -1 times 0 -1 times 0, oh, -1 times 0, it would be 0. So the total would be positive 30 for this pixel, right? Similarly, when you move the filter somewhat more into the right side, you will find when you multiply, you will get a positive 30 for this pixel. Should be like this, right? So when you move the filter to even more right side, you will get a, because all the values are 0, it would be 0 for corresponding to this pixel value, right? Similarly, you can calculate that all the values, all the other values would be like this, right? So only the middle section of the image have a higher values, which is corresponding to the vertical edge in this image, right? So this is the vertical edge that is detected by this edge image. All the other values would become 0, right? Similarly, you can apply the filter uh, when the color is increasing, right? So in the earlier case, you can find uh, the, the intensity of the color is high in this side, and it has suddenly dropped in this level, and it was in a uh, level of 0. This would be the 0, and this would be 10. So the color was suddenly dropped at this edge. This is the opposite of that. So the earlier the value was 0, and it was suddenly increased at this edge, and it became 10 from this edge onwards. So this would be 10, this would be 0, right? So once you apply the same filter as the earlier filter, right? The same filter is applied with the convolutional operator, then you will get a, then still the edge image would detect the vertical edge, but with negative 30, right? But in the earlier case, when the original image was reducing the color in the vertical direction, in the vertical edge, it was positive 30, which is a white color edge that was detected in the vertical image, vertical edge image. In the new vertical edge image, it is a very dark black output of vertical image edge was detected, which is having the minus 30 value, right? So this can be a problem when you are trying to detect the edges in when the color change is different from for different directions, right? So instead of you directly using this edge image, actually you can use a uh, modulus operator. That means you can take either, if it is larger positive value or negative value, you can, once you apply the modulus operator, it will become a positive value, right? So if you apply this plus 30 to a modulus value, it would be plus 30. So still it would be a white color output in the edge. And if you are having a very large negative value like negative 30, and when once we apply the modulus operator, it would become positive 30. So still it would become a bright color, bright white vertical edge that would be detected even when the uh, direction of change of color intensity is different in either direction, right? Either it is from high to low, or it is low to high. That is how the edges are detected using the convolutional operator, right? Similarly, you can uh, identify not only the vertical edges, but using this kind of horizontal filter. As I explained earlier, you can use this kind of filter to identify horizontal edges, right? So in the original intensity is high, and in this edge, if it was reduced, right, this filter would get a positive value. Once you apply the modulus sign, so either way you can detect a positive edge image to detect the vertical edges. Actually, you can use much advanced versions of this horizontal filter, where you can give much higher weight. So this is a vertical edge detector, right? It's known as the Sobel filter. It's a modified version of the filter which we have used up to now, which is a modification of the vertical edge detector, where uh, instead of having plus one plus one plus one, it is using, instead of plus one, it has, instead of plus one, it is using plus two, right? In this pixel, instead of plus minus one, it is using minus 2, right? So that means it is giving a much higher weight to the middle section value. So the scientists have found that this is giving a higher accurately better edge images than the original uh, vertical edge detector, right? And there are much advanced ones. Some of them found that not 1 to 1 but 3 10 3, minus 3 minus 10 minus 3, those are known as Shah filter, right? It is another variation which is also a vertical edge detector, right? So different people have found different kind of filters to detect vertical edges. Similarly, they have found different filters for vertical edges, sorry, horizontal edges, diagonal edges, and so on. Right? Not only the 3 by 3 matrices, but they have found 5 by 5 filters. Right? So if you are using, uh, if you want to by processing a large image, and if you are trying to get better outcomes, you can use 5 by 5 filters or 7 by 7 filters or sometimes 9 by 9 filters, right? So now you will see, right? So there's all these values are generally used as odd numbers, right? Not 4 by 4 or 8 by 8 are used, right? Because then only you can apply, you can get a middle value, right? So when you have a middle value only, then you can have the output image value, right? So otherwise it's difficult to have the middle value, right? So that is why we are using odd numbers for the as the dimensions of these filters, right? So there are different forms of edge detection filters that were developed by different people, and the problem was that how to have the best set of filters was not a complete problem, right? So after the innovation of machine learning, what they found was, instead of defining different weights for each of these filters, like 1 1 1 or -1 -1 or 1 2 1 1 -1 -2 -1 3 10 3, and those are the weights, right, that we are applying in this filter. So if we can, instead of giving these hard coded values by previous experiments, having these values from the previous experiment, what if we can let the filter to learn itself, right, using a machine learning model, right? So instead of having so when you are using the filter and we are giving each of these filter values as parameters to be learned using a neural network with backpropagation, that would be working better, right? Because we don't know actually what would be the best values for each of these filters, right? So that was the birth of convolutional neural networks, right? So all the filter types that we have learned earlier were developed in the earlier uh, times of computer vision, where the scientists themselves have set some values for these sharp filter, so Hubble filters and so on, each of these filters. But now we only specify the dimensionality of the filter, like 3 by 3, and then we set some initial values for uh, these filter values as a weight initialization. Then for each of this image, we try to generate a new image, and then we try to uh, update these filters using backpropagation, and we try to find the best values for each of these weights, so that you can have better filters when you are applying it in the on the real world images, right? So that is the idea of convolutional neural networks. So unlike the uh, fully connected neural networks, fully connected feed forward neural networks that we have learned earlier, we are not applying uh, each of these x values corresponding to each of these pixel to a set of neurons. Instead, we are applying this filter, weight filter, to all of these pixel images one by one with a sliding window using the, so which is known as the convolutional operation, right? And then we try to learn the best values for these weight values, so that it would be giving the best resultant image, right? That is, in this way we learn the weight values, and using this learning technique is known as convolutional neural networks, because you are using the convolutional operation on the image, right? Actually, this is how the input image is convoluted into the second level of neural layers, and similarly you can apply the second level of neural layers, neural values, to another filter, and generate the third layer, and so on, right? Similarly, you can have multiple convolutional layers, so that you can actually have multiple layers in the convolutional neural network, like in the fully connected neural network. So the idea, so now you don't have to deal with many number of weight vectors, weight values, like 3 billion or something like that. You only need to learn 9 weight values for the large image, right? So how large the image is, you don't have to worry about the size of the image. You are only trying to learn 9 weight values in this filter, right? Actually, in the practical world, you are not learning a single filter, but you can learn multiple number of filters, so that it can learn for different features, right? So when you find that the 9 is not a sufficient number of parameters for your model, you need more parameters to be trained to have higher accuracy. You can increase the number of uh, filters that you are using. So when you are using 2 filters, you will get 18 weights, and if you are increasing more number of filters, you will get more and more number of weights to be trained, right? That is how you can tune the number of parameters that you are using in the convolutional neural network. So the advantage is that now you don't have to worry about the number of pixels in the image, or because you can control the number of parameters that you are learning in the convolutional neural network independent from the number of pixels in the image, because we are using the same filter throughout the image using the convolutional operator, right? So we have discussed that when you are applying the convolutional operator to an image, say if it is the image size is n by n, and if the filter size is f by f, then the convoluted image would be smaller in size, right? So it would be smaller than the n by n image. It should be n minus f minus 1 times n minus f minus 1 times image, right? So definitely the convoluted image would be having a smaller size, right? So if you are having multiple layers of the convolutional operator, you would find that the size of the image would be reducing more and more, so that you will be losing more and more edge related information from the neural network, right? So that is a problem, right? Actually, when you have having uh, deeper neural networks with many number of deep layers, this is a very serious problem, right? So that is solved, or that is going to be mitigated using the technique known as padding, right? So this is what we are doing, right? So in the earlier image that we said that if we are using this kind of image, the edge image, original if the If the original image is in the dimensions of 6 by 6, right, then the edge image would be having the dimensions of 4 by 4, right? But instead of letting the size get reduced, you can add another set of pixels around the original image known as the padding pixels, right? Before applying the convolutional operator. So once what you do is you apply the added pixels and at the values of 0 to each of these pixels for all the newly added pixels, and then once you apply the convolutional operator, you will get the edge image which is also having the dimension similar to the earlier image, right? So this should also be 6 by 6 in dimensions, right? So then the information would be preserved in the edge image by simply adding this padding pixels. Actually, not only a single layer of padded pixels you can add, but you can add 2 layers or 3 layers of padded pixels so that the uh, edge image or the second outcome image would be having the same size of the original image, right? So when you are using no padding, or that means when you are allowing the image to be reduced when it comes to the second image or the output image, so this type of convolution is known as valid convolution, right? Because there's no padding used, right? Which we have explained before the padding section, right? So once you apply the padding so that the resultant image or the resultant matrix is also having the same dimensions of the original image or the original matrix is known as same convolution, right? That means we can add when you are adding a filter of size f by f, right? Which is generally an odd number. That means, as I explained before, when you are adding a filter, we are using 3 by 3, 5 by 5, 7 by 7 kind of filters, but not 4 by 4 or 6 by 6 filters because they are odd numbers, right? So when you're using the odd number filters, you have to add a padding, number of padding layers equal to the value of f minus 1 divided by 2, right? That means if f is 3, or if it is a 3 by 3 filter, then if is 3, then f minus 1 is 2 divided by 2 is 1. Uh, that means 2. 3 minus 1 divided by 2, it is 2 by 2, it is 1, right? So if it is a 3 by 3 filter, you can add a single layer of padding, single layer of pixels around the original image that are having 0 value, so that it would be, you can have a same convolution where the resultant image or the resultant matrix would be having the same number of uh, pixels or the same number of values as the original matrix, right? That is known as the same convolution. And the other thing is that when you are using this convolutional operation, uh, let me just clear the um, that we have drawn earlier. Say you are using, say now, so don't think about the padding, right? So just think about the original image, right? So when you are applying the convolution, we said that first we apply the filter like this, and then we apply the filter like this by simply moving your filter by a single pixel to the right side, right? And then we come to the, and then we go here, and then we go there, and then when we come to the next row, we are coming down only by a single pixel, and then we can apply it into this set of pixels, right? So actually this number 1 of shift is not a mandatory number, right? You can actually pass to two pixels at a time when you are moving your filter to the right or to the downside, right? It can be 2, it can be 3, or any number of pixels when you are moving to the next uh, convolutional operation, right? So what we are trying to do here is that you can assign how many pixels that you are moving at a time. That is known as the stride, right? So generally, if you don't specify the stride, it would be 1, right? So that means we are using 1 pixel. We are skipping 1 pixel at a time, right? This stride is represented by S, right? So when you have multiple number of strides, this is known as strided convolution. And when you are having higher number for stride, you can have much more smaller uh, output matrix than the original matrix when you are using it without padding, right? So suppose you want to shrink the information from the original image to a very smaller number of pixels in the second image, so that what you can do is you can increase the stride from 1 to 2 or 1 to 3, so that your resultant image or the resultant matrix would be much smaller compared to the original matrix, right? So in order to find the uh, strided convolution matrix dimensions, you can use this uh, dimensions, right? So when you are having an original image with the n by n dimensions and apply it to the f by f filter with the stride s and padding p, then the strided convoluted image would be having dimensions of n plus 2 p minus f divided by s plus 1 of the flow value. Sorry, it's known as flow value times the same value, right? So the n plus 2 p minus f divided by stride plus 1 flow value. Flow value means uh, when you have uh, a floating value which is not a full integer, you round it to the lower number. For example, the flow of 3.2 is 3, right? Actually, not we are rounding to the closest integer, but to the lowest integer. So the 3.2 is between 3 and 4, right? Between 4 and 3. The flow means we are rounding to the 3, right? So that is why we got 3. Suppose if it is 5.8 and we are trying to find the flow of 5.8, it would be between 6 and 5, right? When it comes to 5.8, this is a value between 6 and 5. So in the flow means you have to round it to 5, right? The flow value would be 5. So this is how you calculate the flow value. So when you compute the dimensions also, or whatever the value you get, you have to round it to the lower integer, right? That is how you compute the dimensions of the strided. So that is how you compute the strided convoluted image, right? So when you try to do apply it in a convolutional neural network, this is only a single layer that which we have learned up to now, right? So we said that instead of learning have hard code in the weight values, we have the variables, weight variables in the filter, right? And also we have to learn a bias, right? And then we multiply it with the input pixel or the input feature matrix, right? It's like if you consider these values like x value, and these weight values like w values, and this b as b, the output would be like and then once we multiply this value, take the convolution with the weight values and plus add the bias value, and then you have to apply the activation function, generally ReLU activation function, and this is the full operation of a convolutional layer. In a convolutional neural network, there can be multiple convolutional layers and plus some other layers as well, right? So we will be learning what are the other types of layers. For now, what you have to learn is that once you have the x values like 3, 0, 1, we multiply each of these values with the w values, right? 3 times w1, 0 times w2. So if when you are applying the filter like this is how you apply: 3 times w1, 0 times w2, 1 times w3, 1 times w4, 5 times w5, 8 times w6, and so on. And finally we add all these values with b, the bias value, right? So this whole thing can be represented as uh, xt w, right, plus b, right? So then it can be applied to the ReLU activation function, where you will get the final result of this convolutional layer, right? So in a convolutional neural network, we said that we can have convolutional layers, and we said that it can contain not only a single convolutional layer, it can contain multiple convolutional layers as well. And in a convolutional neural network, there are not only the convolutional layers are there, right? There can be other forms of layers as well. And other types of layers is known as, sometimes there can be fully connected layers, generally at the end of the convolutional neural network. There can be softmax layers, and there can be another types of layers known as pooling layers, right? So when you want to reduce the size uh, of a matrix, right? So when it comes to convolutional neural networks, we said that we can have many layers, right? So actually, when you are using this convolutional operation in a convolutional neural network, it is not always about having the uh, original image and filter and having the edge image or something, but it may be some corresponding to some intermediate layer, right? So you get some matrix, you multiply it with this weight matrix in the filter and at the bias, and apply the activation function, and then you get the output of this layer, right? So that is the general idea of a convolutional layer, and you can have multiple such layers, right? And suppose you want to reduce the size of the dimensions in each of the layer, right, after the convolutional operation, then you can apply this pooling layer. Pooling means once you get the so this is another form of layers different from the convolutional layers, where in this layer you don't learn any parameters like w or b, right? We don't learn any of them, right? This pooling operation is a operation which is independent from any learned variables like w or b, right? So this is somewhat computationally less expensive compared to uh, convolutional layers. So what here we does is, so when you get a matrix like this, which is a 4 by 4 matrix, right? Once you get a matrix like this, what we do is we if we want to pool it into 4 pools, right? 4 pools means we can pools the pixels into different colors. For example, these 4 pixels are pooled to the blue color. These 4 pixels are pooled to the green color. These to the red color, and these 4 pixels to the yellow color, right? So taking the pool is actually form of taking a certain aggregate value or the representative value of the pool. So one of the widely used pooling technique is known as max pooling, where you take the maximum value out of this pool, out of each of these pool, and take and get the final output matrix, right? So suppose you take this pool, the blue color pool. So if you are using max pooling, what you do is you take the 4 values 9, 2, 2, 4, and find the maximum value, which is the 9 value, and then we apply it in the resultant matrix. Similarly, when you take the green color matrix, you get the pooling value, which is the 7 value, and you give it as the resultant matrix value. For the yellow color also, you take the 8 value as the pooled value, and for the red value also you take the 6 as which is the largest maximum value, and take the output, right? So sometimes there's another form of pooling known as average pooling, where you take all these values in. If you take the blue color, for blue color pool, you can take 2 plus 2 plus 9 plus 4 divided by 4. So this is the average value of this pool. So this is the, and you can use this average value for as the pooling value as well, right? So for the green color also, you can get a pooling value and apply it into the output value. So that is known as average pooling. But generally, with most convolutional neural networks, we are using the max pooling in most of the cases, right? Because max pooling is actually computationally also it is less expensive, and it is much more suitable because when you once you have applied any convolutional layer, for example, if you are using it for edge detection, right? So the edges are the values that are having very high values, right? So if you want to find what is the edge value, so edge value is the maximum value, right? So all the other values are not relevant. So taking only the large value or the maximum value is sufficient to represent this pool, right? So that is why the max pool is used in most of the cases, right? So we said that, right? So when you are detecting an image like this, right? So the higher, when it comes to this edge image, you can detect the edge values in the high intensity values only, right? All the other low intensity values can be ignored, right? So that is why when we are using a max pooling operator, after the convolutional layer, you can get a summary of the edges that were there in the original image, right? That is the idea of using max pooling. So because the idea of max pooling is to reduce the dimensionality, we are not using padding when you are using max pooling. And when you are computing the resultant matrix dimensions, you can use the same formula that is used uh, for convolutional learning, for convolutional uh, operator as well, right? So, so you can use this trident convolutional operator, right? So without, when you are having zero padding, right? And that is how we are going to, so we can have a stride in the pool, and the filter, if it is 2 by 2, right? Because this the filter is 2 by 2, and the next pool is we stride by 2 pixels, right? So that is how we move to the second filter, right? Second mask value, right? So we are using 2 by 2 stride. and the filter is 2 by 2, and this is how the resultant pixel resultant matrix would look like, right? So here we are not using any padding because the idea of using max pooling is to reduce the dimensionality, right? So the filter values can be the final matrix values can be computed as same as the convolutional strided operators, right? Strided matrix resultant values. So let's go into the summary what we have learned, right? And when we are learning about convolutional neural network, so in simple terms, we call convolutional neural networks as CNN, right? So when you say CNN, just to understand this, we are talking about convolutional neural network. That is a tradition. The convention of calling the convolutional neural networks. In CNS, you can have three types of layers. One first type is the convolutional layers, and you can have pooling layers, and you can have fully connected layers. Uh, and in most architectures, so there are well-known convolutional neural network architectures of which we'll be learning in the next lesson. Sorry. So in most convolutional neural networks, we are following the layers in the following manner. Like we are having several convolutional layers and pooling layers one after the other. Convolutional layer, pooling layer, convolutional layer, pooling layer, convolutional pooling layer, and so on. And then we finish with the sequence of fully connected layers at the end. That is the common way of implementing a convolutional neural network. Right? So when you are having a soft for classifiers, right? So we can use softmax classifier at the end like this, right? Convolutional layer, pooling layer, convolutional layer, pooling layer, fully connected layer, fully connected layer, fully connected layer, and then the finally the softmax layer to give the classification value, right? So this is a example case that you can see that, right? So in here you can see there's a X-ray or some scanned values from radiological data set, right? And then you are giving the inputs into this layer like 256, 256 by 32 uh, layer, and then you can see the dimensions are getting reduced, right? And these light color values are known as convolutional layers plus batch normalization and railway activation. So we haven't discussed how actually we can use batch normalizations as well for the regularization purpose and the in order to handle the problems like vanishing gradient problems and so on. And after each of the convolution layer, you are using max pooling layer and so on, right? So in one after the other, we are using convolutional layer, max pooling layer, 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 and then we can have many flattened layer. Flattened layer means fully connected. So this is about actually we are not without having multiple dimensions. You can have a single dimension vector, right? And then from this vector you can apply the fully connected layer with dropout regularization, and then finally you can apply a softmax layer for classification, right? This is a sample convolutional neural network. Okay, that is all for today, and if you have any questions you can ask.